Let's consider constant heat flux surface condition first. Where we have our convective heat flux is a constant. Now, back to our duration here. For a tube, the perimeter is constant. With a constant heat flux, uniform mass flow rate, no phase change, constant specific heat. Under a constant heat flux condition, everything here is a constant. Just must under the constant heat flux condition. If it tells me the gradient is constant, which means it's always linear. It varies linearly along the tube length. If we consider the mean temperature at the location of X, and let's minus where the mean temperature of the inlet over the length where it varies, that's X. It always has the same slope here, constant slope, as the ratio of perimeter convective heat flux over mass flow rate and the specific heat. Then we can do a little bit of rearrangement here to get the mean temperature distribution under constant heat flux condition. So if I times X both sides then plus the mean temperature at the inlet, I have my mean temperature equals what we have at the inlet plus the constant gradient times how long it varies in the length. This is equation 8.40 in our textbook. And the TMI, that's the mean temperature at the inlet. We will have TMO later. That's the mean temperature at the outlet. This is super classic. The book solves the entire differential equation to end up what we have here, the equation 8.40. But we utilized what we have been taught in first class, energy rate balance. And we understand the heat transfer mechanisms inside advection, convection. Then we can obtain the same solution without solving the complex differential equations. I hope after the final, of course they will be tested, but after the final, when you guys deal with the complex problems in your future professional career, this is super powerful. This is the ultimate goal, the engineering tool. Whenever you have a problem, think first, what about I define my control volume first, and then establish energy rate balance. I asked Patricio some question during my PhD research. Then he replied the exact same. Why not you go back and define your control volume? That's it. That's the main goal of this class. You forget about all the complex correlations. They're all tabulated. But with this energy rate balance, you can understand, you can design, you can create your own equations by understanding the essence inside. That's the conservation of energy. Talk too much. Let's now, with this equation, let's think about, go back to what we have at the beginning. Now we have our temperature. I want to know how it varies along the length of the tube. I have a very stupid question. Does the constant heat flux give us constant surface temperature?
No.
Why?
Because if it's constant surface temperature, the heat flux will decrease as time goes on because the water heats up.
Yes, smart. Yeah, we do the mean temperature first. Now it starts at some initial value, which is the mean temperature at the inlet. And we know under constant surface heat flux, it changes linearly. And this gives us the mean temperature of the fluid, Tx, Tmx. How about our surface temperature? This, based on this equation, we know mean temperature of the fluid varies linearly. As suggested, surface temperature should go up. How it gets reflected in our curves here? They say at the beginning, it may be a little bit above what we have, because we consider heating case. Surface temperature is above the mean temperature of the fluid. We know for convective heat flux, it's H times temperature difference. I know here we have our Tm, right, mean temperature. If I do a little bit math here, surface temperature is just simply by what we have for the fluid inside. Don't write this down, that just help you understand. And the ratio of convective heat flux over our H. This is constant because we assume a convective heat flux is constant. How about H? That's the last figure we learned on Monday. How does H vary along the tube length? Decrease, then to 0? No, then to at which point it will remain constant? Similar entry length, right? Yeah, exactly. Then we know, okay, it will be divided into half parts, and we say here is fully developed. Then our H will remain constant. Here is the entrance region, H decrease. H decrease because it's but the constant convective heat flux is constant. So Ts keeps growing at the entrance. Something like that. But once we reach our thermal entry length, H remains constant, and it does not vary anymore. I will erase this, and it's become parallel because this difference now is constant after we reach our fully developed region. Is that clear? It's connect all those graphs we learned all together. I erase this. And the temperature difference is the above curve gives us the curve for surface of the tube. This is our Ts minus Tm. What's the maximum value then? If we have a constant heat flux of surface, what's the maximum temperature difference between tube and internal flows? It's here, right? It's remain unchanged as the constant heat flux over that the convection coefficient once it reaches the fully developed region. Then it's because as we keep heating it, the temperature, both temperature, keep going.